Good evening. We're going to kick off this Introduction to Meteorology course by discovering the atmosphere. So we're going to start off with Chapter 1. This particular image shows you what the Invitation to the Atmosphere by C. Donald Ahrens and Robert Henson. This is what the cover looks like. So this 8th edition is what you should have for the course. All right, so let's move right along to the next slide. Let's talk about things here with the atmosphere. Generally, what is the atmosphere? The atmosphere is a delicate, life-giving blanket of air surrounding the Earth. And without the atmosphere, Earth would not have lakes or oceans or anything. And air protects us from the sun's rays and provides a mixture of gases that allows life to flourish. You know, we have 78% nitrogen, 21% oxygen. That comprises the troposphere, which is our closest layer of the atmosphere, closest to the ground. That contains all of our weather, the troposphere. So it's a 78% nitrogen, 21% oxygen, and just the right mix. The other 1%, by the way, is just other gases such as neon, argon, water vapor, even some CO2 in there. The radiant energy from the sun, that is what drives our everyday weather patterns. The sun is our primary source of what causes the weather. All right, and as with any scientific course, what we need to talk about briefly is the scientific method. So generally with the scientific method, there's a general format you'd follow, I guess to put it in better terms. First thing you want to do in scientific method is pose a question. Perhaps you observe something like the sky color is red at night, a reddish tinge, and you notice that a red sky at night, generally the weather's nice. You know, so maybe at that point you say, well, is the weather always nice when the sky is red towards sunset or in the evening? So that's posing a question. You're looking at an observation of the natural environment. You're posing a question about that environment. Then you're going to go ahead and put forth a hypothesis. Now, a hypothesis is just simply an educated guess. An educated guess why you think something occurs the way it does. Third, you want to predict what the hypothesis would imply if it were true. So what would the result be if your educated guess or hypothesis was actually true? And then you would want to move then into carrying out tests to see if the prediction is accurate. So we use a scientific method quite a bit when dealing with the atmosphere, especially with the weather. You know, you see this put in motion when the TV weathermen, for example, when the TV meteorologist puts up that forecast model, you know, for upcoming weather forecasts into the future. They're using the scientific method and, you know, for looking at the computer models and determining what a particular storm might do, for example, a hurricane, where it might make landfall. And they're going to go ahead and watch how the weather plays out to see if that educated guess or hypothesis is true. You know, the forecast would be your educated guess, and then you would carry out tests to see if, through the observations and what really happens, to see if that prediction is accurate. All right, so this is a nice look at a beautiful looking sky. We got some higher cirrus clouds, beautiful view of the ocean. This again would be the ground truth. This would be you formulate a hypothesis, and then you basically see what actually happens. This is a great picture, by the way. All right, so now we're going to talk about weather, climate, and meteorology. So we need to define these three terms so you get a better general idea of what weather is, what climate is, what meteorology is. So weather is simply the condition of the atmosphere at any particular time and place. Now, some of the elements that we typically think of when we think of the weather would be the air temperature, the air pressure, sometimes this is known as barometric pressure, the humidity, the clouds, precipitation, visibility, this is basically how far you can see in the horizontal, and then the wind. These are all very important elements that comprise weather as a whole. Climate, on the other hand, this is the average weather that we'd expect. A great way to remember the difference between weather and climate is weather is what you get, Climate is what you expect. So for example, when you're planning a trip to go somewhere, say you're flying to the west coast of the United States, you want to know in San Diego what the general weather is, what you normally expect, how you would pack your clothes, for example, certain times of the year. Is it going to be cooler? Is it going to be warmer in San Diego? Well, you would look at the climate. You would look at climate is simply the weather elements observed over a specific time period. Usually that's a 30-year time period is the climate. Accumulation of weather events, and over that 30-year time period we also throw in weather extremes such as record heat waves or record cold spells of winter. Earth and its atmosphere are dynamic systems that are constantly changing. That's one thing you definitely want to keep in mind throughout the course. You know, the weather is always changing in the mid-latitudes. State of the atmosphere can change in a matter of minutes, and an example of this when we talk about weather would be a tornado, for example, a thunderstorm that, you know, maybe the day started out nice and sunny, but as the day progressed, next thing you know, you see a wall of darker clouds starting to move into the area, and next thing you know, you got a severe thunderstorm, and perhaps it produces one of nature's most violent storms, the tornado. So keep in mind that Earth and its atmosphere are dynamic systems. They're constantly changing. That's what makes weather forecasting so challenging. Now, what is meteorology? Okay, meteorology is simply the study of the atmosphere and its phenomena. All right, inventions and concepts involved. Here's a little history involved with the meteorology. 340 BC, Aristotle came up with the Meteorologica. 1843, one of the key ways to communicate weather forecasts was through the invention of the telegraph system. In 1920, a major discovery occurred with air masses and weather fronts. The concept of air masses and weather fronts was developed by the Norwegian school. 1940, upper air balloon observations were launched. We started sampling the upper atmosphere with these huge weather balloons. 1950, numeric models and weather predictions, those started coming into play. And then 1960 was when we first started launching weather satellites into space for monitoring, for example, storms such as hurricanes from a distance. Here's a great look at one of those tools that we typically see, especially on TV today, and that is the weather radar. Typically we talk about Doppler weather radar, and that's what's mainly used. Here's showing you some very intense thunderstorms just to the east of the Indianapolis, Indiana area, as denoted by the redder colors on this. This is a reflectivity image showing you some strong thunderstorms. All right, satellite, you know, we talk about being able to sample weather from remote methods, and one of these remote methods is via satellite. You know, we talk, there's a really good book out there called Isaac Storm, and that was really about the 1900 Galveston, Texas hurricane. At that time in 1900, there was no such thing as a weather satellite, being able to observe the clouds and the structures across the remote locations of the Earth, such as the ocean areas. So 1960 we started launching our first Tyros 1 into orbit. We were able to finally see the clouds, you know, from space. We get those nice pictures that we see so we can identify storms, especially with hurricanes. We're able to alert the coastal populations of an impending storm days in advance. The satellites have got really sophisticated now. You know, now we're into the GO-16, which is a geostationary type of satellite. With geostationary satellites, just keep in mind that those are satellites that travel at the same rate as Earth spins, and they continuously monitor what is taking place beneath them. Meridians are generally defined. When I talk about lines that are termed meridians, I'm talking about longitude lines that generally run north-south. If I talk about parallels, they refer or measure latitude, so just kind of keep that in mind. Storms of all sizes. You know, with satellite imagery, we're looking at storms of all sizes. They could be ranging from the middle latitude cyclonic storm systems. When I talk about those type of storms, the mid latitudes, I'm talking about storms that form outside the tropics. Stuff that, you know, the type of storms that we typically see across the United States, especially in the fall and winter time. Storm systems in general can consist of hurricanes, thunderstorms, and tornadoes. So these are all types of storm systems. Looking now at here's a satellite image. We're talking about satellite imagery and the importance of it. You see in the bottom left-hand part of this image, there's a little donut hole there, and that is a hurricane in the eastern Pacific Ocean. There's also frontal systems across the Midwest U.S. here. This is showing you a mid-latitude storm system over the United States. So you can see that clouds are very important in identifying different weather features. And then what about a weather map? If we took a glimpse at a weather map, usually the TV meteorologist will throw this up on the nightly news. You'll see weather map. You'll see weather map elements such as wind, which wind refers to the horizontal movement of air. Wind direction, keep in mind that wind direction is the direction from which the wind is blowing. I emphasize the word from. So make sure you realize that wind direction is from. Okay, so if I were to say that the wind is indicated as northerly, that would mean the wind is blowing from the north. If I were to say the wind was blowing from the south, that would be a southerly wind component. Wind speed is the rate at which air is moving past a stationary observer. That's all that wind speed is. And then fronts, and then don't really worry about these are introductory terms. We're going to get much more in depth on these in future chapters. But fronts are boundaries that separate warm and cooler air across which there is a sharp change in temperature, humidity, and wind direction. And again, we will get more in depth on all these concepts as we progress. Chapter 1 is more of a introduction to a lot of the different terminology. A glimpse at a weather map. This again is showing you different types of frontal systems. Also on here we have a red L over Minnesota. That indicates an area of lower atmospheric pressure. The blue H's are higher atmospheric pressure. And then you have these numbers on here next to these little station plots or circles, and those are your air temperatures in degrees Fahrenheit. And of course you have your frontal systems over the Midwest, and then you also have the areas of precipitation in green there. Looking now at, this is a beautiful picture here. We're just kind of throwing a type of cloud in here known as a cumulonimbus. And again, you're going to learn about this as we progress in the course. Cumulonimbus is basically a thunderstorm cloud. That's the one that produces quite a bit of lightning. I was living in the Pensacola area myself for about 2 years, and wow, it's quite a dynamic environment down there with those thunderstorms in the afternoon. You get the sea breeze to come in off the Gulf of Mexico. But thunderstorms are a really interesting form of storms that nature creates for sure. Here's an example of a radar image, again just showing you what a thunderstorm would look like on a radar. Generally the color scheme is the reds and the oranges are your heaviest thunderstorm activity. The lighter greens and the blues are less intense precipitation. So now, how does weather and climate impact our lives? You know, obviously it plays a huge role in our plans, our daily activities. From what we wear each morning, right? We usually want to know what the temperatures are, or if it's going to rain that day, or if you live in a colder location, if it's going to snow, that could impact business hours if it's a big snowstorm, or you know, you really want to know because you might be traveling on the roads. It impacts crops, how much crops are produced each year, utilities, how much money do we spend on electricity, what's the demand every winter season for heating, or in the summer season the cooling. It's going to impact our pocketbooks and how much we spend. Health effects as well. You know, there's something known as seasonal affective disorder, SAD, out in the Pacific Northwest and especially into Alaska. And this is a condition in which it's cloudy a good majority of the time, and it impacts people's moods, psychological impacts. Other physical health impacts would be, you know, people that have arthritis with changing barometric pressure and impending storms. The violent impacts through big time storms such as hurricanes and tornadoes that can level homes and change communities forever. And then fog. You know, weather and climate as far as fog, that has a huge role. I lived out on the Central California coast for a while, and the fog was really thick there, and it really impacted people's lives and how fast they could travel along the interstate going to and from where they needed to go. Here's a gentleman coming out, and you can see how high this is up on him. Um, these cars are pretty much buried in this mess. He's got a shovel in his hand. You know, there he is. Here's another major impacting event here that could change communities and lives. This is an example of a tornado, which is basically a violently rotating column of air in contact with the ground is a tornado. This could have huge impacts, especially on the Central Plain states, Tornado Alley. And then this is some of the remnants of tornadoes. You know, this could cause fires. It could level homes. It could do some of the strangest things. You see cars flipped over here, and this impacts people's lives forever. Look at this little graphic here. It shows you the different weather events on the bottom axis. Severe storms, the number of events are in red for each category. The total cost is just astounding on the impacts of weather in our lives. You go on the left there on the y-axis, the number of events are up that y-axis in the vertical. Shows you severe storms, the number of events, and then the total cost involved. Then you've got tropical cyclones. They impact the United States every year. Droughts, flooding, wildfires. Have a really bad wildfire going on in the California region right now. Winter storms, and then freezing. So this just shows you, and by the way, these costs are in total billions of dollars there on the right-hand side. So, for example, severe storms can cost up to $700 billion in damage. And that's just really impressive when you think about it. All right, so now let's talk about the different constituents of the Earth's atmosphere. Generally, the Earth's atmosphere is a relatively thin gaseous envelope, and it's composed of mainly nitrogen at 78% and the oxygen at 21%. There are smaller trace amounts of other gases as well, such as methane, carbon dioxide, argon, neon, krypton. Krypton not enough to kill Superman at all. So it's not that dangerous, but just realize that almost 99% of the atmosphere is within 30 kilometers of the Earth's surface. So if you were to look at a beach ball, for example, the Earth's atmosphere might only be that top layer of the beach ball, that really thin layer. No definite upper limit because it just becomes thinner and thinner over time, the atmosphere. The early atmosphere, that was composed mostly of hydrogen and helium. There was outgassing which occurred, outgassing of carbon dioxide, which is a CO2, and H2O, which is water. And that occurred from the cooling center of the Earth, the outgassing, where these gases came out through vents or openings in the Earth's crust. And once this outgassing of carbon dioxide and the water interacted with particles, it caused rain. And then as that rain fell down, the rain accumulated enough to form lakes and oceans. And then, in turn then, lakes and oceans and water in general are great carbon dioxide reservoirs. They absorb carbon dioxide very well from the atmosphere. Plants evolved during the early atmosphere, and those generally, when you have plants, they usually produce oxygen to form basically today's current atmosphere. Various gases are present in today's atmosphere. Keep in mind we have nitrogen. Again, I mentioned that was 78% by volume. Oxygen 21%. And then that remaining 1%, really, water vapor, that's a very important gas that plays a big role in our weather. Carbon dioxide, that's a big type of gas as far as greenhouse effect and global warming. The ozone, a very important gas. That's really important in that once it's in the upper atmosphere, especially the stratosphere, it generally results in protecting us from the dangerous ultraviolet radiation from the sun. Aerosols, there's a lot of different aerosols. Examples of that would include dust particles. Over the open oceans, you have sea spray, and that releases some particles, some salt particles into the atmosphere. Pollutants as well. We create a lot of pollutants and add those to the atmosphere. So there's a lot of different gases out there that compose our present atmosphere. All right, and then just a quick graph here. This is table 1.1. Generally, again, just a breakdown of the percentage by volumes of nitrogen, oxygen. There's your percentage of argon at 0.93%, and then you see neon, helium, hydrogen, xenon. other gases there too. Okay, and the particles, like I said, I mentioned those: dust, soot, and then chlorofluorocarbons and hydrofluorocarbons as well. So here again, it's just a rehash of the different processes now that make up today's atmosphere. What goes into it? So the general waters dissolve the carbon dioxide. You get chemical weathering of rocks. Photosynthesis, that's a process whereby a plant converts solar energy into food for that plant. And in the process of photosynthesis, the plants take in carbon dioxide and then they release oxygen. Dissolving of CO2 and carbon dioxide, the burning of plants, that adds chemical aerosols into the air, burning of those plants. And then respiration, volcanic activity can add sulfur dioxides, a lot of stuff that comes ejecting out. The ash and the sulfur dioxide can have a major role in the weather. And then fuel combustion from major plants. Here's a composition of today's atmosphere. This is showing you carbon dioxide. Now, in 1958, we had a carbon monoxide monitoring location set up. We have an instrument up there, Mauna Loa, on the island of Hawaii, the big island of Hawaii. And since 1958, it's been monitoring the carbon dioxide output into the atmosphere. And as you can see by this upward trending graph, starting in 1958, the bottom left, at that point in time there was 315 parts per million of carbon dioxide. Now, past 2010, basically in about 2014, we were up to nearly 405 parts per million of carbon dioxide. So you can see a dramatic increase in the CO2 into the atmosphere since we have started observing this back in 1958. Taking a look at this is the ozone hole as of October 2nd, 2015. The total amount of ozone. So in the 1980s, no one really realized this, but something known as chlorofluorocarbons, they're abbreviated CFC. These particular chemicals were in refrigerant, were in hairsprays, air conditioning. Those type of processes created this chlorofluorocarbon, these CFCs. Once those CFCs get into the atmosphere, for example, if they were to rise on rising air currents, what they do, CFCs, is they tend to destroy ozone. And ozone is very important for us, again, as I just mentioned, because it protects us from the harmful rays of the sun, especially the ultraviolet radiation rays. So these CFCs put a major hole in the ozone. Now, we have counter-corrected since the 1980s. A lot of the companies now are producing products that don't have the CFCs, and that has helped shrink this ozone hole down from what it was. It was even bigger than what this diagram is showing you back in the 1980s until we really discovered it. The vertical structure of the atmosphere, now we're going to turn to that. All right, we're going to look at how air pressure and air density, what they are. All right, so what you need to realize is density is just the number of molecules in a given space. You can actually do a formula for density. Density equals mass divided by volume. That's the actual formula for it. You may remember it from earlier science classes, perhaps. The pressure is the amount of force exerted over an area of surface. So just think pressure equals force, the amount of force over an area. Generally, what you really need to know is atmospheric pressure. It will decrease or become smaller with an increase in height. So as you go up in the atmosphere, if you were to go into a hot air balloon and start at the ground and maybe perhaps go up to 10 miles above the surface, you would notice a steady drop in the atmospheric pressure as your balloon continued to rise higher and higher off the ground. So here's the vertical structure of the atmosphere, just kind of showing you. Now that diagram on the right shows you the 14.7 pounds. 14.7 pounds per square inch is the standard atmospheric pressure. All these little white dots, they represent air molecules. And you look how compact they are towards the surface and how they become thinner and more spaced farther apart aloft. There you see air density and air pressure is showing you the curve on the left. and how it's decreasing and getting smaller with altitude. And that's generally the case. Here's a look at the vertical structure of the atmosphere, and just kind of showing you again how temperature changes. That red line there, that is the, actually that red line is the pressure. That's just showing you how pressure decreases with height. We're referencing Mount Everest at this particular point. But if you notice, basically the percentages are there to show you that 50% of the atmosphere pressure is contained below 5.5 kilometers. And then 90% is basically from about 17 kilometers down. You get above that and the atmosphere really thins out. Now, air temperature, that's normally going to drop or decrease from the Earth's surface up to an altitude of about 11 kilometers. We generally determine the temperature by looking at what's known as the lapse rate. And this is the rate the temperature will change with height. In this case, it is normal for air temperature to drop as you go up, away from the ground, up into the atmosphere. Now, there are occasional cases where the air temperature may actually increase or get warmer with height, with altitude. In that case, that's known as a temperature inversion. Rate the temperature increases with height is the temperature inversion. And we'll go into a couple different methods of how this happens as we progress through the course. And we're getting closer to the end of the first chapter here. Cover a couple more topics, so hang in there. Atmospheric layers. Make sure you know the layers from the ground up. The troposphere is the layer that's closest to the Earth's surface. This is where the weather, all of our weather occurs. So we technically are at the bottom of the troposphere on the ground here. That's where we live. The stratosphere, a very important layer that's above the troposphere. It's the second layer of the atmosphere. And this is where you have the ozone molecules that generally will destroy, basically will not allow the ultraviolet radiation from the sun to make it through to the Earth's surface. Without ozone in the upper stratosphere, we would have probably a lot more cases of skin cancer. Those harmful UV rays would cause a lot more sunburns for us here on Earth. So the ozone is a very important gas. And the absorption of the solar radiation by the ozone molecules actually causes the temperature to increase with height in the stratosphere. Now the mesosphere, that's our coldest layer of the atmosphere. Meso, just think of middle, the middle sphere. Thermosphere is the next layer above that, and thermo, think of heat. So that's the hottest layer of the atmosphere is in the thermosphere. And then we have something known as homosphere, heterosphere, and ionosphere. And then homo generally means same, hetero means different. So if I talk about homosphere, I'm talking about a uniform mixture of gases. A heterosphere, that's where we have a wide range of a mixture of different gases. And then the ionosphere is an area up in the thermosphere which is very important for long wave radio communications. So ionosphere is also the area where you would see the auroras, which are really cool. So here's a breakdown graphically, again showing you the order of the layers of the atmosphere. That red line on the graph here just shows you temperature. And so you notice on the bottom there I have temperatures listed. If the temperature line skews to the left, that means the atmosphere is getting colder with height. If that red line kind of goes to the right, that means temperatures are warming with height. And you'll notice how the mesosphere is the coldest layer of the atmosphere, how the temperatures drop off rather rapidly, especially in the middle to upper portion of the mesosphere. The thermosphere, that thermosphere does contain the ionosphere, and that's where you typically see the aurora, which is usually you have to go up towards the polar areas, northern latitudes to see the aurora, but it's really cool to see that. Here's the layers of the atmosphere, and this is the lapse rate. Now, the lapse rate, generally temperatures will drop at a rate of 3.5 degrees Fahrenheit for every 1,000 foot climb or 1,000 foot rise above the ground. So you notice for every 1,000 feet, these numbers here, 1,000, 2,000, 3,000, that's in feet. And then on the right you have how the temperature is changing for every 1,000 feet. And you notice a drop of 3.5 degrees Fahrenheit for every 1,000 feet. So in this case, we're starting out with a temperature of 46 degrees Fahrenheit at the surface, and by the time you get up to about 6,000 feet, temperature is only 25 degrees Fahrenheit. So you can see how that drop off occurs. Alright, and then this is just showing you again the layers. Generally, when you have an active sun, that usually emits a lot of solar radiation particles, and that can interact with the upper thermosphere, and that would result in the auroras. It can also have a major impact on our communication systems here on Earth. Okay, and it's showing you the differences in the altitudes also between the homosphere, the heterosphere, and then the ionosphere, like the depth of those here indicated by the arrows. So in summary, to close chapter 1, the first video on the course, our atmosphere is rich in nitrogen, oxygen, and smaller amounts of other gases. And the atmosphere is composed of various layers. We talked about from the troposphere all the way up to the thermosphere. And then the very top layer we didn't really talk much about, but that's called the exosphere. Meteorology is simply the study of the atmosphere and all of its related phenomena. Weather and climate influence our lives in many ways, which we talked extensively about. And that wraps up the first lesson. That wraps up the first lesson on the introduction to meteorology. I hope you enjoyed this, and looking forward to continuing on in the semester.